In this lesson, we are going to talk about prime and composite numbers. Now, historically, finding prime numbers was very difficult. There are infinitely many of them, so we needed a method to do it. And that's where Eratosthenes, a Greek mathematician, comes in. He developed an algorithm for finding prime numbers. So Eratosthenes historically is known more for his contributions to geography than to mathematics, but this is one huge contribution he had. A sieve is something that actually filters things out. And so what this method does is it actually filters through all the numbers, and the only ones that come through are prime. So we're going to use Eratosthenes' method to find all the prime numbers between 1 and 100. We'll use this grid of numbers here. The steps are written on the left. So the very first thing we're going to do is shade in 1. It's neither prime nor composite. Our next step is to circle the next number in the list, in this case 2. And once we've done that, we're going to shade in all multiples of 2. By being multiples of 2, we know that they cannot be prime numbers. So we're going to shade in all of those numbers here. Now that we've shaded in all multiples of 2, we're going to go right back to the start of the chart and circle the next unshaded number. In this case, that would be 3. Now that we've circled 3, every multiple of 3 cannot possibly be prime because it's divisible by 3. So we're going to go through and we're going to shade in all the multiples of 3. It's worth noting that some of the multiples of 3 are also multiples of 2, so many of them were already shaded. We're going to continue this pattern now, so we go back to the start of the list and we'll circle the next number, which is 5. And now we have to shade in all multiples of 5 because they cannot possibly be prime. We return to the start of the list and circle 7. It's the next number that hasn't already been shaded in. And once we have circled 7, we're now going to go through the list and shade in all multiples of 7 because they, again, cannot be prime. You'll notice there aren't too many numbers left that haven't been shaded in. So we've just shaded in the multiples of 7. Now all the numbers that remain here are the ones that have passed through the sieve. So they are the ones that are not multiples of 2 or 3, 5, or 7. And so these numbers highlighted in red are the prime numbers between 1 and 100. Now as an exercise, I want you to take 3 single-digit prime numbers. You can pick all 3 of the same number or 3 different numbers. Write them in the boxes on the back of your page, 1 in each box. Then you're going to take those 3 primes and multiply them together and write the result in the box below. Now once you've completed this task, unless you picked the exact same 3 prime numbers as someone else, you will all have a different number from one another. Feel free to compare with the people sitting around you. The reason why you all ended up with a unique prime number is due to the fundamental theorem of arithmetic, one of the governing rules of mathematics. And what the fundamental theorem of arithmetic states is this: every natural number greater than 1 is either a prime number or can be expressed as a product of a unique selection of prime numbers. So each of the numbers that you came up with, if you had the numbers 2, 3, 5, and you multiplied them together to get 30, that is the only selection of prime numbers that will get you a result of 30. So you can only multiply together 2, 3, and 5 to get 30. That's the only way you can make it. So it's a unique selection of prime numbers that multiply to get you up to 30. So either you have a number that can be expressed that way, or the number has to be prime on its own. The big question students have now is, why isn't 1 a prime? Most of the time we're clear why 1 isn't a composite number. It doesn't have more than 2 factors. But if we look at the definition for a prime number, it has to have 2 distinct factors, one in itself. Now the number 1 is only divisible by itself. And so you can't count that as being 2 distinct factors. And therefore it's neither prime nor composite. I guess that's why they say that 1 is the loneliest number.